Hello and welcome to Insight Ophthalmology. This is Dr. Amrit welcoming you to another basic lecture. Today we are studying the visual acuity and Snellen's chart testing. Apart from that, we shall also be discussing the components of visual acuity, the components of vision and the Logmar testing. So before you understand the concept of visual acuity properly, we should understand that what is meant by visual angle. The visual angle is the angle which is subtended by an object that we are looking at the nodal point of the eye by this object. So if this is the object present in the visual field, the physical dimensions of this object, in particularly the height of this object, and also depending upon the distance at which this object is located, this object will be subtending an angle or will be making an angle at the nodal point of the eye, and this angle is referred to as the visual angle. Now, you may ask what is meant by the nodal point? The nodal point is roughly located between the anterior 2/3 and the posterior 1/3 of our crystalline lens. So if you understand what is meant by visual angle, now I will tell you what is meant by visual acuity. Now, in a very loose language, or to describe very simply, visual acuity is basically the measure of ability of the eye to distinguish between the various shapes and the details of the object which are given to it at a given distance. So in other words, it is the resolving power of the eye. The resolving power or the resolution means to be able to distinguish two objects as two separate objects in a space. So if we have object A and object B, two present in our visual field, we should be able to distinguish these two as two separate objects, and that is called resolution or the resolving power of the eye. To give a proper definition of the visual acuity is actually the reciprocal of the minimum resolvable angle measured in minutes of arc for a standard test pattern. So I told you what is meant by the visual angle. So for a very minimum amount of visual angle, we'll be able to resolve, and that is called a minimum resolvable angle. The reciprocal of that minimum resolvable angle and the units for that is minutes of arc will give you what is meant by visual acuity. So what are the components of visual acuity? Now there are a few terms that you should understand before you understand the depths of visual acuity. What is meant by minimally detectable? What is minimum separable, minimum cognizable, and minimum discriminable? The minimum detectable means that the ability to determine whether or not an object is present in the visual field. That means you are just detecting the presence of the object in the visual field. That means if this is the visual field, whether this white dot is present or not, whether this white line is present or not, and again this black dot and black line are present or not in the visual field. So that is called the minimum detectable acuity, right? So for this kind of acuity, the limit is 1 arc second. Okay, next. Now here is the other term which is called minimum separable. Minimum separable, as I told you, two objects which are separated in a space, and you should be able to identify them as two separate objects, right? So there are two, like for example here we have two dots and they are separated by a distance. So this is called minimum separable, and this is also referred to as a resolution, right? So what is a threshold or what is a minimum angle, visual angle that the object should subtend at our eye so that the objects are at least minimally separable? The angle is 30 to 60 seconds of an arc, right? So this is the minimum angle of resolution, and the reciprocal of this angle only will give you the visual acuity, because visual acuity is the resolving power of the eye. So similarly, in the second picture you can see there are 5 lines, and you're able to tell that there are 5 lines and they are separated. That means they are not overlapping. So what I mean by minimum angle of resolution is that if the angle or if the visual angle subtended by two objects, okay, falls below this below this minimum angle of resolution, that is below 30 to 60 seconds of arc. That means if the angle subtended is about 20 or 10, then you'll not be able to resolve that object in the space. You'll have actually you will perceive it as overlapping or one single object instead of perceiving it as two different objects. Next is once the brain is able to resolve a particular object, then it can also recognize it, right? So when we give the patient or give an examinee certain objects which are familiar to it, like letters E, A, B, like that, or some symbols like this, okay, then we are testing the recognizing ability of the patient, that is called minimum cognizable. So not just the detection and then resolution, but also the recognition ability of the patient is tested during the visual acuity. And then this is usually not done, and this is called the minimum discriminable. Minimum discriminable means that it is the ability to determine whether or not two parallel or straight lines are aligned in a frontal plane. So if you see, there is this one line and there is this two lines, and you can see there is a small offset between that. That means the two lines are not aligned in a straight line. So this, if you're able to detect this minor offset of the lines, then this is called hyperacuity or super acuity, right? So this is even more advanced acuity. Now, just for the completion's sake, a common question which is asked is, what are the components of measurement of vision? So the components of vision are the visual acuity, the visual fields, contrast sensitivity, color vision, and stereopsis, that is the binocular single vision. Now, let us talk about the Snellen's chart, because we know this is the basic chart that is used in the clinic for determination of the visual acuity of the patient. So the Snellen's chart was developed by Professor Hermann Snellens in 1863. As you can see in this picture, it actually consists of a series of black letters, okay, and they are arranged on the whiteboard in lines. And you can see these lines as you go down the chart, the size of the letters is progressively diminishing, right? So at a given distance, each letter will subtend an angle of 5 minutes at the nodal point of the eye. So that is why I was telling you what is meant by the visual angle, because these letters at a particular distance, they are also going to subtend a particular visual angle, and that visual angle for Snell's chart is about 5 minutes. So let me explain it to you in detail. Now, each letter on the Snellen's chart is actually called an optotype, and each optotype is made in such a way that it fits a square, right? So if you take a square like this, the letters have to fit in the square, okay? So that is the reason why we are not using all the alphabets. There are certain particular alphabets only which can actually fit in a square configuration. Only those are taken in the Snellen's chart. Now, the letters in the Snellens are actually devised or designed in such a way that they have a breadth that will subtend an angle of 1 minute at a nodal point of the eye in a particular distance. Suppose, so this is a letter E, and you can see each part of this letter E. Suppose if you consider only this part of the letter E, this will actually subtend an angle of 1 minute of arc, right? Now, the entire letter, however, if you take, will be subtending an angle of 5 minutes of arc, right? So each letter is designed in such a way that it fits a box or a square, and the sides of each letter are actually 5 times the breadth of the constituent line. So the constituent line, say, is 1. So if this is 1, the entire thing is 5. So if this is 1, the entire thing is about 5 minutes of arc. So this is how each letter is subtending an angle of 5 minutes of arc at the nodal point of the eye. So that is very important. Now the question is that at what distance are they subtending that angle of 5 minutes at the nodal point? So each letter with its height or size is devised in such a way that, for example, the topmost letter, which is written suppose 20 by 60. Okay, so 20 by 60 means that the topmost line will be able to subtend an angle of 5 minutes of arc at a distance of 60 feet only. Okay, and the 20 by 40 means that this letter will subtend an angle of 5 minutes of arc at a distance of about 40 feet, and this small letter, that is 20 by 20, will be able to subtend this at 20 feet. So that is very important. So each letter is going to subtend that angle of 5 minutes, which is taking the arbitrary for the Snellens at a particular distance only, and that distance is represented in the denominator of the chart. So now there are two notations for the Snellen's chart. So we have the metric system in which we use the 6 by 60. So the top letter is the 6 by 60. Then we have 6 by 36. Then we have 6 by 24, 6 by 18, 6 by 12, 6 by 9, 6 by 6 and 6 by 5. Okay, so the denominator means that each letter, that means this letter H, will be able to subtend a nodal point at the nodal point 5 minutes of arc at the distance of 60 meters only, and 36 means at a distance of 36 meters it will subtend that angle. Similarly, we have another system in which we use the units feet. So we have 20 by 200, 20 by 100, 20 by 70, 50, 40, 30, 25 and 20 by 20. So this chart over here is actually comparing the feet system with the metric system and its equivalents. Now the question is, why is that testing distance of 6 meters or 20 feet taken for testing in the Snellen's chart? So the testing is basically done at 6 meters. Okay, this we all know, or it can also be referred to as 20 feet from the target. Now the reason we are doing it is because at this distance of 6 meters, it is considered that the divergence of the rays is very less, and most of the rays which are entering the eye, they are entering parallelly. So that is what we want in refraction, the rays to come at a parallel distance in a parallel way, and therefore we are using this distance of 6 meters. So now the question is, what does it mean by 6 by 6 or 20 by 20? So before that, I will tell you what is meant by this notation. So if we consider this 6 by 6, okay, yeah. Yes, so here 6 by 60, the topmost line 60 means that a person who is having normal visual acuity will be able to see this line even at 60 meters. So that means although we are testing the patient at 6 meters, this patient is able to see this line even at 60 meters, right? So if someone is having a visual acuity of 6 by 36, it means that this patient is able to see this line even at 36 meters, although we are testing at 6 meters. Okay, so that is what is the meaning of the notation. Now, what if someone can see 6 by 6 or 20 by 20? 6 by 6 or 20 by 20 means that he has almost perfect visual acuity. That means he is able to see that 1 minute of arc which is close to the theoretical diffraction limits. That means we know that each letter, the width is about 1 minute of arc and the entire thing is about 5 minutes. So even that 1 minute he's able to resolve. So that is a very good visual acuity. So as I told you, the distance, now let us see how the patient is actually tested. He's tested at a distance of about 6 meters. So let us see how. So patient is seated at a distance of 6 meters from the Snellen's chart. You already know why. And then the illumination of the chart is also very important. It should not be less than 20-foot candles. And now the patient will be tested with each eye separately, one eye at a time. And the visual acuity is recorded as a fraction. Usually the worst eye, the eye with the worst visual acuity, is tested first. Now the visual acuity, as I told, is tested in fraction in such a way that the numerator will actually tell you the distance at which the patient is currently present from the chart, okay, which normally is 6 meters, and the denominator will tell you the smallest letters that the patient is reading accurately. So if the person gets a vision of 6 by 6 say in right eye and 6 by 24 in left eye, what does it mean? It means that the patient was standing at a distance of 6 meters, and by standing at a distance of 6 meters he's able to read this line over here. That therefore his vision is 6 by 6. Okay, that means his vision is almost normal. Now what about this in the left eye? In the left eye, standing at 6 meters, he is able to read only up to this, and therefore the visual acuity is 6 by 24. Okay, so if a normal person stands at 24 meters, he will be able to see this line. However, this patient is able to see up to this line only at 6 meters, and therefore this is definitely a compromised visual acuity, and this is 6 by 24. So I hope that it's clear how to represent this in the form of fraction. Now, what if the patient is not able to see this line as well? So if the visual acuity is 6 by 60, fine. But what if the patient tells you that he cannot see even the topmost line? Then what do? You ask the patient to get up and walk towards the Snellen's chart till that line becomes clear. Now, depending on the distance at which the patient is present from the Snellen's chart, you are going to give him the visual acuity. As I told you that the numerator will tell you the distance from the chart. So if the patient is standing at 5 meters and is able to read the topmost line, then the visual acuity will be 5 by 60. If he's standing at 4 meters, so it will be 4 by 60, 3 meters, 3 by 60, 2 by 60, and 1 by 60. Now, what if the patient is not able to identify even at 1 by 60? Now, next, what do? Now, you have to show the patient your fingers and tell him to count them. So that is called counting fingers. And this is again done at different distances. So if the patient is able to do at 3 meters, it is called counting fingers 3 meters. If he's counting the fingers correctly at 2 meters, it is CF 2 meters. Then if it is at 1 meter, that's CF 1 meter. And sometimes you might have to go very close to the patient face and show your fingers, and that is called counting fingers close to the face. Now, sometimes the visual acuity will be so worse that the patient will not be able to count these fingers even close to the face. Now, then what do? Then you have to move your hand to and fro in front of the patient, and that is called hand movements. So by moving the hands, you're asking the patient whether he's able to perceive at least those hand movements, and if he's able to do that, then that is called hand movement positive. If not, it's called hand movement negative. And then again you proceed to show the patient light. So it is believed that even in the worst visual acuity, at least the patient will be able to perceive the light sense and will be able to tell whether the light is being shown into the eye or not. And mind you, this has to be tested again uniocularly. You have to ask the patient to close his one eye properly with his palm, not with the fingers, because then the light can pass through the fingers and the patient might be giving you a false positive response from the other eye. So in this, you shine a light in front of the patient eye and then ask him whether he's able to perceive the light. And here it's often advisable to use the brightest source of light, and it is usually said that the light coming from the indirect ophthalmoscope is the brightest source that you can use for testing the perception of light. Okay, so if the patient is able to perceive the light, he is given PL positive, and if the patient cannot perceive the light, then it is recorded as PL negative, that is perception of light negative. Next, suppose if the patient is not able to do even PL positivity or PR, usually, or to tell you, the PL and PR, that is the perception of light and projection of rays, are usually tested together. That means if the PL positivity is there, suppose if the patient has PL positivity, then what you do is you take a light and then you shine it in all the directions, in 4 directions of the patient, and ask the patient to point out to you from which direction the light is actually coming. So this way you are actually testing the 4 quadrants of the retina, and then you are going to give the report. So if the patient is PL positive, you shine the light at 4 quadrants, and suppose the patient is able to see the light which is coming from superiorly, you write as PR plus. That means the projection of rays is coming nicely from the top, and then from the right side, from the left side, that means nasal and temporal, and also from the inferior. So the notation can be given like this. This is how you represent the PR, projection of rays. Next, coming to the decimal notations. Yeah, sometimes the Snellen's fraction can be converted to decimal. So that is how you give it. So 20 by 20 will be about 1, and 20 by 30 will be 0.7. So this is just a basic division. 20 by 40 is 0.5. Now, for the research purpose, we have another chart, and that is called the Logmar chart. Now, this is used basically for academic and research purposes and not so much in the clinics. This is a modification of the Snellen's chart. So how is it modified is that in Snellen's chart, we know number 1 is that each letter is subtending an angle of 5 minutes of arc at the nodal point. However, here the minimal angle of resolution is actually changing in each line by a unit of 0.1 log unit, right? And they have an equal number of letters in each line, and they use and this is tested at a distance of about 4 meters. In contrast, the Snellens is using a testing distance of about 6 meters. So that's important. So you can see about every line has about 5 letters. Okay, so the number of letters are same. However, the visual angle that they are subtending will keep on differing from the previous line by a unit of 0.1 log units. So this is the comparison between the feet notation, meters, and the logmars of the Snellens and the Logmar. So you can see 20 by 20 is 6 by 6 in the metric notation of the Snellens and 0.00 in the logmars. So that's all for today. Thank you and have a nice day.